We're on the third page, front to back, related rates. On the falling ladder problem, the bottom of the ladder is pulled away at 3 feet per second, so that means it's kicked away at 3 feet per second. That's a rate. So I'm going to call this the x-axis and this the y-axis. So it tells me instantly that dx, with relate to time, dt, equals 3. How fast is the top sliding down when the bottom is 15 feet from the wall? We'll wait for that until the very end, and they want to know how fast it's going down. So dy dt is what we're looking for. This is going to be a Pythagorean theorem problem, and notice the ladder's length is constant. So I'm going to set up the Pythagorean theorem, x squared plus y squared equals 25 squared, because that is constant. Pop the derivative, that's going to give me 2x dx dt plus 2y dy dt equals 0. Notice if I divide everything out by 2, I just get x dx dt plus y dy dt equals 0. And now I'm going to substitute in everything I have. But before I do that, at the instant the bottom is 15, I need to know how high it is. So I have to set up the Pythagorean theorem. And that's going to be the square root of 25 squared minus 15 squared. And that's going to equal 20. So I have all the information I need. That 20 is not the dy dt. That 20 is this moment in time when the base is 15 feet away as it's sliding away. The top of the ladder is going to be 20 feet high at that moment in time. So I take x and plug it in for x, so 15 goes there. Dx dt I already have, that's my 3. Plus y, which is 20, times the variable, what I'm looking for, dy dt. And that's equal to 0. That's going to give me 45 equals negative 20 dy dt. And then I divide both sides by negative 20. And that's going to give me negative 9 fourths. Negative 9 fourths feet per second. Number 48, the dreaded cone problem. Water is going into, so the cone is filling up at a rate of 2 meters cubed, that means volume, per minute. How fast is the water level rising? So they want to know what dH dt is, and it's going up, so it's probably going to be a positive. When the water is 5 meters deep, that is a moment in time. I'm going to save that for the end. So the volume formula is 1/3 pi r squared h. The deal is they want to know how fast the height is changing. They don't care about r. So I'm going to set up a relationship between the radius and the height of this cone. I notice that r over h is equal to 4 over 16. Simplified is 1/4. I'm going to cross multiply. That gives me 4r equals h. But I need to solve for r because I want to have this in terms of h alone. So r is going to equal h over 4. So my volume, only in terms of one variable, is going to be pi over 3 times the radius squared, and the radius is h over 4, times h. The volume is going to equal pi over 3 times h squared times h is h cubed over 4 squared, which is 16. I'm going to leave that 3 there because I know when I take the derivative, dv dt, with respect to time, equals 3 times the front, which is the power rule. Notice that 3 and that 3 cancels out. So that's going to give me pi over 16, h squared, because I minus 1 from the exponent, dh dt. It tells me that the volume is changing at 2 equals pi over 16 when the water is 5 meters deep. So I put the 5 in for h. That's going to give me 25 dh dt. Now I have a little bit of arithmetic to do. I'm going to multiply both sides by 16. So that's going to give me dh dt equals 32. And then I divide both sides by 25 pi over 25 pi. And you can read your answer in that form. 32 over 25 pi meters per minute. Because it is a height. The walking shadow problem. A light casts a shadow when a man walking away at a rate of 5 feet per second. So this change in this distance from here to here is, I'm going to call x this distance. So they give me the change in x, dx dt, equals 5. They give me that. I'm going to set up a triangle to show that I'm looking for this change in distance. How fast is the derivative, is his shadow. Some people call this length s, but I'm going to call it y. So I'm going to set this up. Notice, his height is 6 feet. So this sets up a proportion. I'm going to say 6 over y is equal to 15 over this whole length, x plus y. I'm going to cross multiply. That's going to give me 15y equals 6x plus 6y. Subtract 6y from both sides. That's going to give me 9y equals 6x. I'm going to solve that for y. That's going to give me y equals 6 over 9. And I believe 6 over 9 can be simplified. 2/3. Y equals 2/3 x. Now, to find out the change in y, how fast is the shadow lengthening, I'm going to take the derivative. So dy dt equals 2/3. The derivative of x is dx dt with respect to time. It gave me dx dt as 5 feet per second. So dy dt, the first part is going to be, multiply that by 5, 10 over 3 feet per second. Now it wants to know, at what rate is the tip of the shadow moving? Well, that's this change, dy dt, and this change, dx dt. So all I do is add dx dt to dy dt. So that's going to give me 5 plus 10 thirds. (25 thirds) feet per second. Angular rate of change. An airplane flies at an altitude of 5 miles. That's its altitude. Towards a point over a man. There's the man. Write theta as a function of x. So there's theta. So I have a SOHCAHTOA. This one's going to be TOA. Tangent equals opposite over adjacent. So tan theta equals opposite over adjacent. But it wants me to write theta as a function of x. So I take the inverse tan of both sides. So that's going to give me theta equals the arctan of 5 over x. That was part A. Part B, the plane speed is 400 miles per hour. So its change in speed is going in. So it's going to be negative dx dt because it's flying to the left. Find d theta dt when x is exactly 10 miles. So I'm going to take the derivative of theta. So d theta dt equals the arctan derivative is 1 plus something squared on the bottom, and that something is going to be 5 over x. And now 1 is supposed to go on top, but I have to take the derivative of the 5 over x. So that's going to give me the derivative of 5x to the negative 1. That's going to equal negative 5x, subtract 1 from that, to negative 2. Negative 5 over x squared. Don't forget, with respect to time, dx dt in the back end. Now I have to plug in all my values to find d theta dt. That's what I'm looking for. So d theta dt equals 5 over x squared. X is 10. So that's going to give me negative 5 over 100. Find a spot to write this large. Negative 5 over 100 divided by 1 plus 5 over 10. Well, 5 over 10 is 1/2, or 0.5 squared, times dx dt. And it tells me dx dt is 400. Technically negative 400, because it's flying into the left. Well, the 400 and the 100 are cancel out to 4. Negative 4 times negative 5, well, that's going to give me 20 on the top, divided by 1 plus 0.5 times 0.5 is 0.25. So 20 divided by 1.25. 16 radians per minute. Or I'm sorry, radians per hour. 16 rads per hour. Okay, what we're going to do here is optimization. So for the oranges and trees problem, wherever I see the word tree, I'm going to highlight green. So I have 30 orange trees, and every additional orange tree, so that's adding 1 tree. And then notice I have produces 500 oranges. And then over here, for every tree I add, 10 fewer oranges happen. So that's going to be minus 10. And I need to set up an equation for this. So I'm going to call this my orange function, O of x. And my green function is going to be 30 trees, but I'm adding a tree. So I originally start with 30 trees, but then I add so many trees. It might be 1 tree, 2 trees, or 3 trees. And every time I add a tree, something happens to the orange count. The number of oranges per tree goes down by 10 per tree. And that's the function. That's the key to this problem, is setting up the function. Next thing I'm going to do is FOIL that out. I use a Punnett. That's going to be 30 plus x and 500 minus 10x. It's going to give me 15,000 plus 500x minus 300x minus 10x squared. So my orange function is actually going to look like this. Negative 10x squared. Notice, negative 10x squared means it's going to have a max. It's going to be parabolic, and they want me to maximize this. 500 minus 300 is plus 200x plus 15,000. The key is to take the derivative and then set the derivative equal to 0. So the derivative is going to be negative 20x plus 200, and that goes away. So I take the derivative and I set it equal to 0. And that's going to give me negative 20x plus 200 equals 0. So 200 is going to equal 20x. And x is going to equal 10. This is a tricky problem. That's not my answer. It asks how many total trees should be planted. So I need to take that 10 and add it to that 30. So this is going to give me 40 trees total. That's the actual answer. The fenced-in yard problem, he has a perimeter, 400 feet of fencing. And he's making these rectangular pens. I'm going to label this whole side over here as x. And this length is y, this length is y, this length is y, and that length is already marked as y. So my perimeter of this fence adds up to equal 400. So I have this x plus this x. That's 2x plus 1, 2, 3, 4 y's equals a total of 400 feet of fencing. I'm going to simplify this real quick and just divide everything by 2 to give me x plus 2y equals 200. Now it wants me to maximize the total area. So the area of this yard is going to be x times y. I'm going to solve this for x and then plug it in over into that area formula. So notice x is going to equal 200 minus 2y. I'm going to plug that value in over here for x. So my new area is going to give me 200 minus 2y times y. Distribute the y. Area is going to equal 200y minus 2y squared. I'm going to take the derivative and then set the derivative equal to 0. So a prime is going to equal 200 minus 4y. Set that equal to 0. 200 minus 4y equals 0. So 200 equals 4y. I get y equals 50. So this length is 50, this length is 50, this length is 50, and this length is 50. That's 100, 200, out of 400 foot of fence, that leaves me 100 up here and 100 up here. What are the dimensions? X and Y. So the dimensions are going to be 100 times 50. 100 feet by 50 feet will give me the maximum area. Another fenced-in problem. This time I have 150 foot of fence. I have a Y, a Y, a Y, a Y, and a Y. But notice I don't have another X because that's a river. No fence needed. So my perimeter is going to be 1, 2, 3, 4, 5 Ys plus 1 X. So X plus 5 Ys equals 150 foot of fence. My area is still going to equal X times Y. Same concept. I'm going to solve this for X. And then plug that value in, 4X, over here in the area formula. Distribute. Take the derivative. Set the derivative equal to 0. Solving for y. I get y equals 15. So this is 15 foot, that's 15 foot, that's 15 foot of fence, that's 15 foot of fence, and that's 15 foot of fence. That's 30, 60, 75 out of 150. That means x has to equal 75 as well. So the dimensions needed are going to be 75 feet times 15 feet. 75 foot times 15 foot. Surface area of the can, they give me the formula, where the height is h and the radius is r. The volume is pi r squared h. What dimensions minimize the surface area of the can when the volume is 16? So this time it gives me the volume. So the volume formula is that, and the volume is 16 pi, and it's going to equal pi r squared h. So I can instantly divide both sides by pi, so that's going to give me 16 equals r squared h. And I have 2 pi r squared plus 2 pi RH equals my surface area. Now I have to determine which one I'm going to solve for, so I'd like to replace that h. So I'm going to solve this over here for h. I'm going to divide both sides by r squared. And that's going to give me h equals 16 over r squared. I take that and I plug it in over here and then take the derivative and set the derivative equal to 0. 2 pi r squared plus 2 pi r times 16 over r squared. The r's are going to simplify, and the 16 times 2 is going to give me 32. I still haven't taken the derivative yet. All over r. Now, to take the derivative of this, I'm going to want to bring that up here, so I can just use the power rule. So I'm going to write this as r to the negative 1. Taking the derivative, so a prime equals 4 pi r minus, because negative 1 times 32 is negative 32, pi, subtract 1, that's going to give me r to the negative 2, but I'm going to throw that downstairs, r squared. The trick is to set this equal to 0. So I'm going to set the derivative equal to 0. So when I do that, I'm going to add the 32 pi over r squared to both sides. So let's see. 4 pi r equals 32 pi over r squared. Multiply both sides by r squared. That's going to give me 4 pi r cubed equals 32 pi. Divide both sides by 4 pi. Finally, I'm going to have r cubed equals 8. When I take the cube root of that, this is going to let me know r equals 2 inches. Now I need to know what the height's going to be. I take that 2 and I plug it in over here. 16 divided by 4 is going to give me the height equals 4 inches.